All right, so welcome to the graphing rational functions video. You can go ahead and start by pausing the video and then graphing the function to the left. All right, you should have graphed a rational function f of x equals 1 over x using the table graphing the points. So you can go ahead and check yours versus mine. And then let's talk about these key features here. So if you need to pause the video to fixtures or to add in your asymptotes, that's what the vertical and horizontal dashed line are, then please do so, and we'll talk about those. All right, so first off, let's talk about the key features of this graph. So first off, we have a vertical asymptote at x equals 0. If you look at our table, it's when x is 0, it is undefined, the output undefined, because when you plug in 0 right here, you can't divide by 0. X will never be 0. So what we have there is a dashed asymptote, a dashed vertical line called an asymptote. We also have a horizontal asymptote at y equals 0. If you think about y, okay, once again, we know that x can't be 0 because we can't divide by 0. But if we plug in 0 for y, it's asking you, when is this fraction going to be equal to 0? And that's never. In order for a fraction to be equal to 0, the numerator has to be 0. So the function also is undefined at y equals 0. Okay. Next, our x-intercept. Your x-intercept is always the ordered pair something comma 0. If you look, we have a horizontal asymptote there, so there is no x-intercept. Now you can actually sometimes cross a horizontal asymptote, but we don't get to that till later. But also remember to find your x-intercept, plug in 0 for y, which is what we did right here, so that's not gonna have a solution. Y-intercept, plug in 0 for x. If we plug in 0 for x, we already know what happens. We get 1 over 0. F of 0 is 1 over 0, which is undefined. So there is no y-intercept. And then our end behavior. So we did end behavior with polynomials. Now we're doing them with rationals. So we're going to say as x approaches negative infinity, and then we're going to look at what the function's name is. It's f of x. We're going to say f of x approaches. And then we're going to look. So as you look left, what's happening to your y values? So if you look at your y values right here, the arrow is not pointing up, the arrow is not pointing down, it's leveling out at our asymptote. So it's approaching 0. As x approaches positive infinity, what's happening to your y values? If you look, the same thing's happening. This is getting closer and closer to the asymptote, so it's approaching the asymptote. So, long story short, if you have a horizontal asymptote, your function should be getting closer and closer and closer to that, so that's what your end behavior should be. Okay, so now we have a slide that's telling us what to do when graphing, okay? So it says graphing rational functions in the form f of x equals, and then notice it's in the form of a rational, and this is standard form of a polynomial on top in that numerator of the rational and standard form on the bottom, okay? So step number 1 is you have to factor the numerator and the denominator completely. So you want it in factored form. You don't want it in standard form, okay? Then you are going to see, so that's step number 1. Step number 2 is right here. I don't like how this is 2 then 3. How dare this be here? Step number 2 is find any holes. Okay, I'm going to fix that for the note sheet for you guys. Step number 2 is find any holes, which are called discontinuities. So what you're going to do is you're going to look for factors that simplify out, and then you would find the coordinate of the hole if they exist. If the function simplifies, you're now using that function for everything else. Okay, that's why it's so important that step 2 and 3 are switched. Next, you're going to find your vertical asymptotes. Your vertical asymptotes make the denominator 0, so what you're going to do is you're going to set your denominator equal to 0 and solve. Next, you'll find your horizontal or oblique asymptotes, and we're not doing oblique asymptotes till tomorrow, so let's concentrate on horizontal asymptotes. Oblique asymptotes will be discussed later. So horizontal asymptotes, what you're going to do is you're going to compare the degrees. It's saying compare n and m, okay? So compare the degrees. So this and this, okay? Back to your standard form. If the degree in the numerator is bigger, then there's no horizontal asymptote, okay? That's no horizontal asymptote, which is what we discuss later, okay? That means there's no oblique asymptote at y equals something, and we will discuss how to do this later, okay? Now, if the degree in the denominator is bigger, then it's automatically y equals 0. And that's what it says here. If the degree in the denominator is bigger, y equals 0, okay? So I like to say it, like I don't like saying n greater than m, horizontal asymptote at y equals 0. I say degree in denominator greater than y equals 0. All right, now what if the degrees are the same? So what if this was like a 2 and a 2 here, a 3 and a 3, or a 4 and a 4? Then what you're gonna do is you're gonna take the lead coefficients and divide them. So you'll have y equals, and then the lead coefficient divided by the lead coefficient. So in this case, it's a divided by c. Okay, so the other things we're gonna ask you for, the x-intercepts, the y-intercepts. X-intercepts set the numerator equal to 0 and solve. That's if it's just one fraction. If there's any add-on, you have to make it one fraction. Number 6, find the y-intercepts by evaluating f of 0. So plug in 0 for x, see what you get for y. Number 7, find a point on each side of the vertical asymptote. So to get the most accurate graph, everywhere you see an asymptote, you're gonna have to find points to the left and the right of it in order to make the graph accurate. And then you're gonna draw, lastly, your hyperbolic branches. I know it seems like a lot for, hey, we didn't do any graphing right there, but we learn as we go, right? So if you need to refer back to the examples at any point, please do so, okay? But yeah, that's what we're gonna do. So we have 1, 2, 3, 4 examples in here. When we get to the the third and the fourth, you should pause the video, try it yourself, and then fast forward or rewind through any points that you don't need help with. Okay, so step number 1 here, I have a rational function. I need to factor the numerator completely and factor the denominator completely. So I have f of x is equal to, the numerator has a GCF of 4, and then we have x squared minus 1, which is still factorable. And then my denominator factors to x minus 2 times x plus 1. So I'm going to continue to factor that. So I'm going to say f of x equals, my numerator still factorable, x plus 1 times x minus 1 for that, x squared minus 1. And then x minus 2 times x plus 1. All right, so now what I'm going to do is I'm going to look to see if this is simplifiable. If there is any common factor from the numerator to denominator, it's simplifiable, and that means there is a hole in the graph, okay? Where is there a hole in the graph, okay? So the hole in the graph is located at, if you set that factor that you just canceled out equal to 0 and solved, so set x plus 1 equal to 0 and solve, you get x equals negative 1. And now you have to write your new function simplified. F of x equals 4 times x minus 1 over x minus 2. You're using this for everything to answer every question. And like what I sometimes tell my students to not do, but to watch me do, is to watch me scratch all of this out and don't come back to it. Don't even refer to it. Because if you're like, wait, what about that? The answer is don't look at it. So I'm going to do that. I'll end up erasing that, but please don't refer to that. Okay, so we need the y value of the hole, so we're going to plug negative 1 into f. So we're going to do f of negative 1, plug in negative 1. You get 4 times negative 2 over negative 3. So you get negative 8 over negative 3, which is 8/3. So the hole is at negative 1 8/3. Next, we'll find our vertical asymptotes. We find our vertical asymptotes by setting the denominator equal to 0 and solving. So that's x equals 2. Horizontal asymptotes, we compare the degrees. The degree in the numerator is 1, because it's like this is like 4x minus 4, right? The degree in the numerator is 1. The degree in the denominator is 1, so it's the same. So what we're going to do is we're going to take a ratio of the leading coefficients. So that's 4 over 1, which is 4. So our horizontal asymptote, y equals 4. X-intercept, set the numerator equal to 0 and solve. So I'm going to set 4x minus 4 equal to 0 or just x minus 1 equal to 0. You get x equals 1. So I get 1, 0. Y-intercept, plug in 0 for x and see what you get for y. In the numerator, I get negative 4. In the denominator, I get negative 2. Negative 4 divided by negative 2 is 2. And then lastly, our end behavior. I can do the end behavior already because I know that there's a horizontal asymptote. So I'm going to say as x approaches negative infinity, comma, f of x approaches the horizontal asymptote of 4. As x approaches positive infinity, f of x approaches the horizontal asymptote of the y value of 4. Okay. So now what we're going to do is we are going to plot everything that we have. We're going to start with our vertical and horizontal asymptotes and the whole. And I do those in one color and then everything else in another color, but you don't have to color coordinate. All right. So I'm going to, do I still have my ability to paste here? No, how sad. All right, I'll do it once and then I'll use it for the rest of them. So what I'm going to do is I'm going to draw my vertical and horizontal asymptotes with which must be dashed lines. I'm drawing solid lines right now, but I'm going to turn them to dashed. So x equals 2, y equals 4. Then I'm going to circle them. Oh, they kind of moved a little. I'm going to hit style. I'm going to make them dashed, and I'm going to make them a little bit, that's too thick. That's good. I'm making them a little bit thicker so that they're easy to see. Okay, good. And I'm going to copy those so that I can paste them down below when I need them. All right, so arrows on the end here. Okay, there's my vertical and horizontal asymptote. X equals 2, y equals 4. All right, now I'm also going to graph the whole. The whole is at negative 1 8/3. That means that there's a gap there. So I'm putting an open point at negative 1 comma 8/3. 8/3 is 2 2/3. So negative 1, 2 2/3. So like right here, I'm going to put an open point. Okay. All right, now I'm going to switch to a different color. I'm going to do blue because that's what I usually do my notes in. And I'm going to graph any actual known points that I have. So I know that there's the point 1, 0 and 0, 2. And that's all that I got, okay? All right, so I know what one of my branches looks like because these asymptotes I have to get closer and closer and closer to. So now it's one swift piece right here that I'm drawing in this, but I have a shaky hand, so I'm going to start off at the hole and get closer and closer to that asymptote, and then up into the left, get closer and closer to this asymptote. But that's one piece. Actually, it's two pieces because it's separated by the hole, but it has one swift movement, and you're jumping over that hole. Okay. Now there is a second branch, but I don't have any more information. So if you look to the left of the vertical asymptote, I have a branch over there, but to the right of the vertical asymptote, I don't. So I have to plug in any of these x values here to get a point so that I can graph another point. So I'm going to plug in 3 into my function. So I have 4 times 3 minus 1 over 3 minus 2. So this is 8 over 1, and I get 8. So I have the point 3 comma 8. I'm going to graph that. And then that's enough to graph one more branch, okay? And you can plug in, and if you're like, oh, I want another one, I want to plug in 4 and see what I get to make it even better. And I get 12 over 2, which is 6, and I have 4, 6 also. You can graph more points to make it look even better, but all you need is one point to know what that branch looks like because it has to follow those asymptotes. Got it? Probably not. We need another example, right? I'm going to erase all this scratch out that I did because I don't want to forget to erase it. Okay, and I'm not going to scratch out this time. All right, here's another one. So first off, if you look, the numerator and denominator are both in standard form. So I'm going to factor. We'll just factor. All right, my numerator is factorable, and it factors to x minus 3 times x plus 2. My denominator is also factorable, and it factors to x plus 2 times x minus 1. Let me double check that. It looks good to me. All right, so now I'm going to look to see if there's any holes in the graph. If nothing cancels out, then there are no holes, and you'd put none, okay? There is a hole in the graph on this one because I have a factor of x plus 2 and x plus 2 cancel. So I'm going to write out my new function before I even write down where the hole is. F of x equals x minus 3 over x minus 1. And this is what I'm using to answer every single question now, okay? So first off, where's the hole? Set x plus 2 equal to 0 and solve, and I get negative 2. To get the y value, plug negative 2 into your new function. So you're doing negative 2 minus 3 over negative 2 minus 1. So that's negative 5 over negative 3, which is 5/3. Negative 2 comma 5/3. All right, vertical asymptote, set your denominator equal to 0 and solve. You get x equals 1. Horizontal asymptote, compare the degrees. The degrees are the same, they're both 1 and 1. So we are going to take a ratio of the leading coefficients, 1 and 1. 1 divided by 1 is 1, so we have y equals 1. X-intercept, set the numerator equal to 0 and solve. You get 3, 0. Y-intercept, plug in 0 for x and see what you get for y. We get negative 3 over negative 1, which is 3. And then our end behavior is as x approaches negative infinity, f of x approaches 1. And as x approaches positive infinity, our y values approach 1. All right, let's go ahead and graph. I'm going to start with my asymptotes, paste, and then I'm going to move them where they're supposed to go. So my vertical asymptote is at x equals 1. And my horizontal asymptote is at y equals 1. I'm going to put arrows on the ends of them to show that they go on forever and ever. Voila. I'll graph the hole right now also. That's at negative 2, 5/3. 5/3 is 1 and 2/3. So negative 2, 1 and 2/3, just above that. I should probably zoom in to make my life easier, huh? That's good. Just above that asymptote there, okay? All right, now I'm going to switch colors because that's what I like to do, not, a must. 3, 0 and 0, 3. All right, to the left of the vertical asymptote, I don't have 2 points. I have a point and a non-point, okay? But that's enough to graph that hyperbolic branch, right? Okay. And then to the right of the, did I say right before it? To the left, I have a point and a non-point. And then to the right, I have a point, which is good enough information. Just make sure you're getting closer and closer to those asymptotes and not bouncing off of them. And that's what your graph looks like. You don't need that table, which is great because you have enough points. All right, you can go ahead and pause the video and try these two on your own. But then if you get stuck at any point, check with mine, or fast forward to the end to check your information, or just check with the answer key that's posted in Schoology. But if you need more help, that's why I'm going to do them also. All right, so I'm going to factor. I'm going to go a little faster. F of x equals, the numerator is x plus 3 times x plus 1. The denominator, two numbers that multiply to give me negative 2 and add to give me negative 1, are x minus 2 and x plus 1. All right, I do have a hole in the graph. Write my new function, f of x equals x plus 2 over x minus 2. This is what I'm using to get everything after I get that x value of the hole. So the x value of the hole is at negative 1, comma, and then plug negative 1 into your function, that function right there. I get a 2 in the numerator, and I get a negative 3 in the denominator. So I have negative 2/3. Vertical asymptote, set the denominator equal to 0 and solve. Horizontal asymptote, y equals 1. X-intercept, set the numerator equal to 0 and solve. Y-intercept, 0, comma, negative 3/2. End behavior as x approaches negative infinity, f of x approaches 1. And as x approaches positive infinity, f of x also approaches your horizontal asymptote. Graphing this, I'm going to paste once again my asymptote. Oh, no. I guess I'm not going to paste my asymptotes because you saw what I just did. Copy. I'm going to paste my asymptotes. Okay. All right, so x equals 2 right there. And y equals 1 right there. Put arrows on the end to show that they go on forever and ever and they don't stop just because I stopped drawing them. Hole in the graph, -1, -2/3, -1, -2/3. There-ish. Ooh, I don't like how small it is. It looks closed. There we go. All right. Points I do know, -3, 0, and 0, -1.5. Right there. Okay. All right, I have enough to graph this piece. So I'm going to draw closer and closer to the asymptote. Make sure you're skipping over that hole. Closer and closer to the asymptote. And then now I need to get a point for to the right of the vertical asymptote. So I'm going to plug in 3 and possibly 4. If I plug in 3, I get 6/1, which is 6. So I have 3, 6. If you'd like to plug in another point, which you can, but you do not have to, you get 7/2, which is 3.5, which I'm not a big fan of, but it's a decimal. But if you felt the need to. Okay. All right. Ooh. Ooh. All right. Once again, if you haven't tried one on your own, this is a good one to try on your own here. It's slightly more difficult because you feel like you're doing something wrong, but you're not. All right, f of x equals, factor your numerator. There's a GCF of 3, and then you have an x squared minus 1. And then your denominator factors to x plus 3 times x minus 3. So that's still factorable, so I'm going to keep on factoring. 3 times x plus 1 times x minus 1 over x plus 3 times x minus 3. And if you look this time, there is no hole in the graph, so I'm going to put none. Okay? Vertical asymptotes, set the denominator equal to 0 and solve. I get x equals 3 and x equals -3, which you can write as plus or minus 3 if you want. Horizontal asymptote, compare the degrees. It's easier to compare them when they are written in standard form. I'm not a fan of not having any y equals 0 where the numerator or where the denominator was bigger. Like if this is a cube right here, it'd be y equals 0. Okay? All right, so compare the degrees are the same. It's a ratio of the leading coefficients, so that's 3/1. So y equals 3. X-intercept, set the numerator equal to 0 and solve. So you have this and this that you have to set equal to 0 and solve. So you get -1, 0 and 1, 0. Y-intercept, plug in 0 for x and see what you get for y. I'm looking at this right here because it's easier to plug it in there. You get -3 over -9, which is 1/3. And then your end behavior, you are following as x approaches negative infinity. Does f of x again? Yeah. F of x approaches 3. And as x approaches positive infinity, f of x approaches 3. I'm going to paste some asymptotes here so I can move them. All right, we have a vertical asymptote. I'm going to copy this and paste another one. Okay, we have a vertical asymptote at x equals -3, a vertical asymptote at x equals positive 3, and then we have a horizontal asymptote at y equals 3. Okay, arrows on the ends of all of them to show that they go on forever and ever. And now to graph what we have. There are no holes in the graph, so we don't have to graph those. I have an x-intercept at negative 1, 0, which is right here, and 1, 0. And then I have a y-intercept at 0, 1/3. And then that's all the information I have. Okay, so I'm going to start with each section. So here's my first section, which is to the left of the vertical asymptote. I don't have any points there. So I am going to pick a point, any of these x values. So I'm going to do -4, and I'm going to plug in -4 and see what I get. So if I plug in -4 in the numerator, I have 3 times -3 times -4 times -1 is -5 over, plug in -4 in the denominator, I have -1 times 7, right? -4 minus 3 is -7, my bad. So I get, in the denominator, I have a 7, and in the numerator, I have 45, right? Yeah, 45. This is not a beautiful answer, so I might end up plugging in -5 also, but it might not give me a beautiful answer either. All right, so when I plug in -4, 7 goes into 45, 6 times with the remainder of 3, so 6 3/7. I'll live with that. All right, so I have -4, 6 3/7, right there. Good enough, right? Gave me a piece, right? I just needed to know, did it look like this or it look like this, right? I needed to know which one it was. All right, in this section here, I do have enough information to graph, okay? Because I have these points in here. And remember, you have to follow your asymptotes. So I know that this looks like a downward facing parabola in here because it's got to get closer and closer to this asymptote, and it's got to get closer and closer to this asymptote. Okay, and then my last piece, I'm going to plug in +4. And if I plug in +4, I have 3 times. Plugging in +4, I have 5. Plugging 3 down there. Sorry, I'm plugging in 4. 4, I got 3, which I get 45 again. And then if I plug in 3 down there, I get, 4 down there, I get 7, so I get 45/7 again, which is 6 3/7 again. No shock to me because it's quadratic. Okay, 4, 6 3/7, and then I have this hyperbolic branch. Okay. All right, so how'd you do? Hopefully not too shabby, but that's it for today.